We are very happy to have Vijay here, who's going to be doing.
Great. Well, thanks very much for coming on day two. Abhijit wasn't here yesterday, and maybe some other people weren't here, so I'll do a brief recap at the very end of the talk and pick it from there. So remember, the beginning of yesterday's lecture started with some motivation for why we want to think about the complexity of quantum dynamics, different fields in which that's useful. And then I discussed one approach to that concept, which is based on Nielsen's computational approach, thinking about time development as a quantum computation and using circuit complexity and the geometry of SU and so on. Then I said that something, well, some nice results you can get, but it's difficult to calculate with. In any case, who knows what complexity means anyway? So let's just investigate some other things. And then we decided to take a look at the idea of thinking about complexity dynamics and something to do with sort of the spreading of the wave function across the Hilbert space. And we came up with some idea that the complexity should somehow describe the spread of the wave function over time in a minimizing basis. Meaning a minimizing basis is as follows. It was hotly debated here yesterday. It's something like this. So what you do is you take some interval of time, and you require that for any subinterval of time, if I take little epsilon time, 2 epsilon, 3 epsilon, all the way up to some duration t, that fixed basis should give you the shortest description over all of those intervals. Right? So it's the one that's going to minimize it over the entire set of things in sequence, right? The shortest one, the next one, the next one, the next one in sequence. And that there is a special basis, the Krylov basis, which is the Gram-Schmidt orthogonalization of the initial state, the Hamiltonian initial state, this sort of power series like this. And you can show that this is the basis that minimizes with that definition of minimization. Okay. We want to define some notion of complexity on this basis. In this special basis, we can write the probability that you occupy a given state or not. And then what you can do is you can measure from that. You can make different kinds of measures. You can make the mean position along that basis. This is the one we'll use because it turns out to be the one that has certain useful applications. But it'd be entirely reasonable to think about the entropy of that distribution exponentiated or higher moments. They haven't been as extensively used because people have found this appearing as an answer to various questions. So they've been using this. But these things are going to appear, I'm sure, in other applications in due course. Yeah. Okay. So fine. Then what we need to do is to find methods for calculating the special basis and measuring the spread complexity, and then see what it's useful for. And today we will spend some time on this thing and part of this thing. And if I don't get, I haven't prepared anything for this under the assumption that I'll be interrupted after every slide and things like this. So we'll see. Okay. So this is what I said yesterday. I will recap quickly again for benefit of people who were not here yesterday, which is that the simplest or most direct method for how to construct this special basis is, as I said, you need to Gram-Schmidt initial state, Hamiltonian initial state, etc. And you can that Gram-Schmidt procedure was nicely described by a recursion algorithm by Lanczos. And it goes like this. You start with the initial state, that's K0, that's the first element of the basis. Then what you do is you act once with the Hamiltonian. And so you act once with the Hamiltonian, and then you have to do some subtractions and some normalization, stuff like this. And then you keep going like this, and that will generate a basis. So there's an algorithm you could employ, and it is in fact employed by the people who do quantum dynamics. So in this special basis, as I also mentioned, this is going to come back for us. The Hamiltonian is tridiagonal, which is to say there is a term which involves going back to yourself, the state changing to itself, one to go to the next state and one to go to the previous state. So the Hamiltonian looks like this. It's basically reducing the dynamics to a Markov process. So any quantum dynamics for any dimensional system, etc., it's reduced to a one-dimensional chain in this presentation, which is, of course, super useful because, one-dimensional dynamics are the ones that we're really most comfortable working on. So that's good. And then I described that there is this kind of, and then you can expand in this basis, find these probability distributions between different basis elements and compute whichever notion of complexity, whether the mean position or whatever you're interested in. That's what I said yesterday. I also did a little riff on, notice that what we've really done is instead of diagonalizing the Hamiltonian, which is what we usually try to do, we've tri-diagonalized the Hamiltonian. You might think, well, that's going to be complicated. But actually, this is a very well-studied topic in linear algebra, how to tri-diagonalize a Hamiltonian, given that some particular vector is kept fixed to be, let's say, 1, 0, 0, 0, 0, subject to that condition. This is the initial state. That's a well-studied problem. And it's called, that tri-diagonal form is called the Hessenberg form. You can check it up in Wikipedia if you like. And there's an algorithm which uses something called a householder reflection, which I also had never heard of before, but turns out to be there. And it's implemented in SciPy and Mathematica. So if you do not wish to understand it, you can even just run the code and it will just work.
And this came up yesterday. Let me ask again, sorry. If you keep that initial vector phase,
yeah, it's supposed to be unique. I think the form is supposed to be up to phases. But the phases,
reasonable then.
Yeah.
but the phases you try to absorb into the you try to make all the numbers positive by absorbing it in this formulation. If you want to match up with this Langshaw's algorithm, you would absorb the phases into the definition of the state of the basis.
Sure.
Up to phases. Yeah. Which at the end we can talk a little bit of phase. I'm slightly confused about why in these formulations the phase doesn't play a more important role, actually, because normally when I think of entanglement is all about phases. Anyway, there's some confusion I have. We've discussed this before. Well, we can discuss this at the end. There's some interesting thing going on there.
I mean, I guess to prove that, you'd have to look at the conjugate of the size, right?
You'd have to look at the conjugate of the size.
Like if you're looking at expectation values of n, then
I think you have to look at the basis elements. And you have to look at what's going on with the basis elements and the shift. So I'll tell you something a little bit later about, instead of looking at these coefficients, looking at the actual basis elements and how they change when you do this, that, the other. So we'll define a quantity called the coherence with a K for Krylov, but it's the relative coherence of the two bases after you perturb the initial state. And that definitely has some dependence on these things. Well, we can talk about that later.
Positive definiteness of Hamiltonian is imparting special property to this diagram of trigonal.
Must do, amongst other things, notice this B2 is B2. So this is a symmetric matrix. Real symmetric matrix.
That comes from hermeticity of positive.
That comes from the hermeticity. Yeah.
And how much cheaper is this method compared to the definiteness?
I didn't say it was cheaper than exactly diagonalizing. I don't know if it's much cheaper than exactly diagonalizing. It's just the form that allows you to describe dynamics starting from some initial state. If you do exact diagonalization, what you would do is you'd find the energy eigenstate basis, project on the eigenstate basis, multiply by the phases. It'll be slightly obscure what the dynamics is because it's just the phases rotating around. So it's a different way of doing things. I don't do enough simulations of dynamics and things like that to be able to tell you how much more efficient or not it is. Okay. But I do know that a lot of people who try to do simulations of quantum dynamics apparently try to do variants of this technique. As I mentioned to you, the thing to be careful about is anything that involves these kinds of recursive procedures like this will involve potential numerical instabilities, because you make a small mistake early in whether then it can blow up. So you have to be careful, do some of the usual things like use double precision, right? If you need so much precision, actually double it, because you're going to need to worry about much later in the chain, and there's things like that you can do. My impression is that at least in our hands, or doing this thing with the householder reflections and everything is pretty numerically stable, actually. And that's probably because whoever wrote the SciPy package has probably optimized the heck out of this in some way. And so you don't have to think about it. Somebody else did hard work. That's probably, yes, please.
The statement correct that in order to get to the three-node basis, we need this trigonal division.
Well, if you get the Krylov basis, the Hamiltonian is tri-diagonal. I think you're asking, can you calculate the basis without going through one of these procedures? Well, I think you're implicitly doing this procedure. I mean, suppose you just do explicit Gram-Schmidt, right? If you do explicit Gram-Schmidt, although it's not immediately obvious to me where the A and B, the Langshaw's coefficients are, I mean, obviously they'll be there, because so I think one way or the other, they're just tied like this. Okay, so that was method one. So now let me describe a second method.
Really sorry, you must go on, but just to physically understand, the fact that it's the spread is minimized in this basis also means, I suppose, that the time-dependent changes in expectation values of
Quantities.
all kinds of observables is most efficiently.
Yeah, so in particular, hi Shiraz. Yeah.
And
So
that would, of course, be sensitive to the phases. It's general expectation.
yeah, so you could put other kinds of probes in it.
Yeah.
And the expectation values of those probes or transition elements,
Yeah.
right? So suppose you kick it at one given time,
Yeah.
right? If you kick it at one given time and ask where does it land, well, that depends on the initial and final state, the phases will not. So very little has been done about that because basically, this has been such it's been productive. Lots of people have had very good results and on many things. So I think there's some time yet to go, and at some point people start thinking about that. Again, I think I mentioned Omkar and his group's work before. One very nice class of things they have shown is through similar means, but there's a sense in which I was going to talk about this in the third lecture, but let's see. In some senses, the most semi-classical, most classical basis, in the sense that they have some particular notion of if you make a basis and you want to spread on that basis, then you can compute the Wigner negativity, which is a proxy for how the efficiency of classical simulation. And they have shown in a very nice paper that the Wigner negativity is minimized in this basis, which is also a very nice thing. It's somehow the most classical basis to describe the evolution. There's something interesting about that, which is what I guess we're in the process of trying to think more about. Really. Yeah. So I'm actually going to go through these methods because, as usual, there are different methods for calculating something, and different methods become useful for different purposes. So we'll just discuss a few methods. So here's the second one. So this is the method using something called survival amplitude. It goes like this. So suppose you have the time-dependent state, and I'm going to write the time-dependent state in the Krylov basis. So in that case, the basis, of course, fixed because you already calculated it, and you've got some time-dependent coefficients. And psi naught is the initial state. So now what I can do, I can write down the so-called return amplitude or survival amplitude, which is the overlap of the time-evolving state, initial state. It's like this, you put in the Hamiltonian there, or the time evolution operator there. And this is basically going to tell you the chance that your state didn't change. Now, also, if you look at it, this is the generator of the moments of H. Now, remember, we've just been saying that the way in which you get higher elements of the Krylov basis is you take H, H squared, H cubed, etc., all the moments, if you like, active in the initial state, and then you have to do some some Gram-Schmidt. So basically, this thing is a generating function. Time evolution is a generating function of that of those objects that you need. Excellent, because then this means that you can take the return amplitude in this way and take the nth time derivative, and that will drop IH to the n and everything. So if you could calculate with some precision the return amplitude, you'd be in good shape, right? You could take some derivatives to get the objects you need and everything. So then now, let me describe, suppose you've done this, and we'll discuss in situations where you can do this more easily, calculate the return amplitude. So suppose I have that, I've already got that in my hand. I want to point out another kind of efficient algorithm you can use, given the return amplitude, to work out all the Langström coefficients, if you like, Krylov basis elements. So remember, we said that in this special basis, the dynamics is basically a Markov chain like this. Okay. So now I'm going to unwrap the chain. The way you should think is that this line is the 0 state. This is the 1 state, the 2 state, etc. Now this is time 0 when I start. This is time 1. This is time 2. And it has this pyramidal structure because at time 0, I'm of necessity in this thing, if you like, in this Markov chain. And at time 1, I'm here or here. There's various things I can do. So if you want to compute the survival amplitude, here's what's going to happen. Actually, I should be slightly more accurate. If I'm talking about a discrete evolution, then, in time step 1, you can be here or here. Time step 2, you can be at state 2, 1, or 0. In the continuous time evolution, of course, you're doing all of it at the same time because you apply h or h squared, h cubed, depending on which term of the power series you have, right? So I'm describing, but you can do on your computer, you can, of course, do the one-step action of the Hamiltonian, 2 steps action of the Hamiltonian, etc. And you can get that by doing the full time evolution and then taking time derivatives. That'll give you each of these pieces. That's the idea. Okay, so you have those moments. Now, here's the unwrapped chain. So here's what we can do. So look at this unwrapped chain. At time t equals 0, I know I'm here. Now, at time t equals 1, or rather, after action of one step of the Hamiltonian, the chance that I'm going to be in the same state in K0 is simply IA naught, because this is the only way to get there. Now, after 2 actions of the Hamiltonian, there are 2 contributions to the chance of being in K naught. I can go I naught, IA naught times IA naught, or I can go IB1 times IB1. So what can I do? First, I evaluate the first moment of the Hamiltonian, and that allows me to read this coefficient out. Then I read out the second moment of the Hamiltonian, and subtract from it minus A naught squared, and that will give me B1. And you can see in this way, there's a simple dynamic programming algorithm you can write to simply just read off the coefficients one by one. Super quick to do. And so basically, if you know A naught to AK minus 1, B1 to BK, there's a unique path. There's a single path where AK contributes to the next moment of the Hamiltonian, and similarly for BK. So in this way, if someone tells you the survival amplitude through some means, then you can compute the moments. Once you have the moments, you just run this algorithm, and you can read out the Longshaw's coefficients, and that will do your job for many things. So this is especially nice for thermal states. And I'm going to show you for thermal states. That's because for thermal states, the survival amplitude is literally the analytically continued partition sum. So there are many, many techniques in physics that we have for calculating the partition sum. So that's super helpful if I can take a thing that's a sort of standard object that we would normally work with and then use that. So here's an example of TFD state. This is a TFD state. We have 2 copies of the theory. And so then I have, exponential weighting and partition sum and everything. So let me time evolve by just saying the left Hamiltonian. And what that basically does is, it'll add a phase, right? It'll add a phase e to the I n t in front of each one of these, which is equivalent to saying that you change beta to beta plus 2it, 2 because of this 1/2. So I've just shifted the beta in some imaginary direction. So now I'm going to remind that the partition sum, if I evaluate the partition sum at beta minus it, it looks like this. If I evaluate the spectral form factor, that's this thing squared. So the survival amplitude, which is nothing but this thing, the time evolved state, overlap with the initial state. If you overlap that, you'll find it's equal to z of beta minus it divided by z of beta. And so the survival probability, which is the thing we've been working with, is basically the square of that. So that's basically like the survival amplitude. That's like spectral form factor with some normalization by the partition sum. I'm just trying to show that there is a relationship, right, between this object, not surprisingly, and other objects, which have been found useful in statistical physics, quantum statistical physics, for studying such objects. So let's put it like this. If someone gave you the spectrum, worked it out nicely, then from that, you could compute the partition sum, analytically continue it. From that, you can read off the survival amplitude. You can take some moments of the survival amplitude and run that algorithm, that graph algorithm that I was talking about, get you the Longshaw's coefficients, and you could work out the spread complex. So that's a second thing that you can do. Okay. So
this will become functions of temperature.
These are all functions of temperature. Yeah. Okay. The next one is even more interesting, I find. And so I'm going to try to show you that there's a direct way in which if you give me the density of states, you can, there's a formula relating the density of states to the Longshaw's, basically the energy spectrum to the Longshaw's spectrum. So I'm going to explain the situation in which you can write down the formula, and then give you a somewhat heuristic proof outline. You can give either a heuristic proof like the one I'm giving you now, or you can be much more careful involving type path through the matrix and things like this. That I won't do. That's a little
Lanchas coefficient with state. Again, the
any state. So which state am I taking here? So the trick here is that you've assumed here some sort of generic state in the Hilbert space, and this formula will not apply to the edges of the Langshausen spectrum. The edges of the Langshausen spectrum are going to get controlled by what the initial state is. But then for a generic state, by which I mean some sort of random superposition of energy eigenstates, what is going to happen is in the bulk of the Langshausen spectrum. So we're thinking about some large N system here. The bulk of that past the initial edge, there's a universality to the coefficients. That's really the argument being made here, but the edge will depend initial state.
But at random and in a fixed energy band?
You can say random in a fixed energy band if you wish, yeah.
So it's basically electrotropic state.
Microcanonical state. It's easiest to think about these things with some microcanonical band that you expand. In fact, almost anything you want here, you can do with an infinite Hilbert space. If you do thermal weighting or something, you can do this perfectly well with canonical ensemble. But if you want to do this reasoning, it helps to first start off with a large but bounded Hilbert space and then write it in terms of that. So that's what I'm going to do. Yeah. We can, of course, imagine that we've bound that Hilbert space with n, and actually there's some thermal weighting. So what I've really done is I've cut off the tail of the thermal weighting in some way, and then I make it bigger and bigger. We've not been very careful about that. I don't necessarily see any obstacle. Right. So what we're going to do is we have some system with a Hilbert space of dimension n, and we're going to take the large n limit. But we're going to start with some finite n. So then remember the way we've described things. It's there's a nice discrete Hilbert space. But then you have the index n of the Krylov basis elements and the Hamiltonians n by n, so on, like that. And I'm going to define a continuous index x, which is little n over big N. And this is some number between 0 and n. Okay. And what's that?
No.
Small n is the Krylov index. So remember, by Krylov index, I mean, we're going to write down this basis, right? K1, K2, K3, K4 for a big N dimensional Hilbert space. So little n must. Yeah. So there's some further subtlety you could have here, which is that suppose, let's put it like this. Suppose you have an infinite dimensional Hilbert space, but you start off with an initial state that has support on some piece of that. Then that's whatever piece of that, the dimension of that piece of that is this n. Yeah. So that's related to the microcanonical ensemble. Okay, so we are going to wind up taking big N to infinity and treating x as a continuous variable in a minute. So in that limit, the claim statement is that if you give me the density of states, and in the continuum limit like that, it makes sense to talk about the density of states. It isn't just a bunch of delta functions. It's given by this formula. So it's an integral from 0 to 1 of this number x. So there's a theta function on top, which is sort of, if you look, there's an energy here, and these are the Langshausen coefficients. I'll explain the overbar in a minute. And underneath, there's a square root form. Those of you who are familiar with matrix model type results will have seen formulae that look like this, sort of like this. And they'll have more to say later. I think there's something deep there, which hasn't been completely dug out. We'll put some more connections on the page later. So there's a bar on top of these, because these A's and B's are not exactly the A's and B's of each index, the Krylov chain, and they've coarse-grained. And so A and B should be understood as a local average in the Krylov chain. Local average in what sense? You should average over a window, which is not scaling with n. So the window size divided by big N is going to 0. But of course, you can make that window very big if you wish. Right? It has to not scale with system size. Okay, so then averaged in that way is what this is. So let me give you a proof outline for how you get this result. So suppose H is a Hamiltonian, and we have taken some piece of the Hilbert space. The states are supporting that piece of the Hilbert space, and A and B n are its Langshausen coefficients. Okay, I'm going to define A of x to be AXN and B of x to be BXN, converting into the continuous coordinate. And I'm going to assume that these things have a continuous large N limit, right? That need not be the case. You can construct examples where they don't. But in many of the examples that we know and love, like in many 2D CFDs and in particles and group manifolds and the SYK model, even in JT gravity, if you start using the spectrum, it has this property. So a better thing to do would be to state, here are some conditions on the theory that allow you to have this property. I can't quite state exactly what those things are. Yeah.
But just out of curiosity, these have been computed in other ways. Maybe you described for, say, the SYK model.
Yeah.
We know that.
Yes. So I'll show you comparisons later. So, you do explicit numerical computation. You do it using the recursion method.
And then you show the large.
And then you show the large N limit, you calculate it, you compare it to this analytical formula, and then you compare.
That's understandable. I was wondering.
Yeah, that's how you verify.
It would be quite a tour de force. Yeah.
Yeah.
Okay. Thank you.
Yeah. Yeah, actually, we'll come back to the SYK models more later. So the way you show this is as follows. So imagine that you've broken up basically the Hilbert space or the Krylov chain as you wish into large blocks of size square root n. I'm picking square root n because square root n is huge. So I can sensibly think about that block as a large matrix, but at the same, I'm going to infinite size, but it's going to infinity slower than system size. So divided by system size is negligible, right? Okay. So in order to have a continuous limit, you're going to have that the A and B coefficients, the Langström coefficients, need to be constant in each block. Because if they were varying in each block, what would happen is you couldn't take the limit and get a continuous difference, right? It wouldn't change continuously. Just do that.
So, sorry.
It doesn't have to be square root. We need it to be large because I'm going to use a fact about large Toeplitz matrices, right? So it doesn't have to be square root. Pick anything you want.
Even when, as you said, you could have earlier when you defined the bars, you said you have some large, but finite.
You can make it order one. Order one, but large. Yeah. So anyway, so if the Langström coefficients are blockwise constant, that means within the block it has a Toeplitz form.
Yeah, why is that so? That in the block they're constant?
Because otherwise, how do you take the limit? If it's varying within the block, you need to be able to assign a unique value of the A and B to each block.
But I thought you're doing that by averaging.
Well, so this is so here in this argument, I'm not doing averaging per se, right? What I'm saying is that within this block, it's constant. So really, you should think about I'm taking the average value within the block is what I will report at the end of the day.
But those two things would be the same. That considering average value in the block and the actual block where things are not constant. I mean, it could be
so as you take the large N limit, the argument is that as you take the large N limit, in order to have a continuous large N limit within blocks of a substantial size, it will have to be constant. Right? So in this argument, which is a little bit waving the hand, the issue is, well, the next block has a slightly different value, so it's not really matching up in the end. So that's why I'm saying it's a somewhat heuristic argument for that reason. It's a physicist style argument as opposed to a math style argument. You can do a separate math style argument, which is sort of much more careful. It will take a page or two to do that and show that the limit exists. And the limit exists and gives you these things. I'm calling this the average value because, it's not, there are actually, in some sense, small variations going on throughout. And what you're doing here is you're averaging this. Also, we're going to wind up comparing this at the end of the day to finite n matrices numerically. And when we do comparison to finite n matrices numerically, of course, we don't have this large n limit. So what are you supposed to compare to? So the idea would be you compare to sort of local coarse grain blocks.
Do you have to make any assumptions about the average when you see that should have good?
Yes, this is assumed in effect that the Hamiltonian is good continuum limit. The statement that this AX and BX have good limits is the assumption the Hamiltonian is good continuum limit.
In terms of the spectrum.
In terms of the spectrum. You mean position space?
There's
no direct bearing on the position space. So for example, if you had a particle on a circle, there's a discrete gap spectrum, but it's continuous in space. So this is a statement about what it should look like in in energy space. It makes no particular commitment to whether you're on a lattice or whether you're in the continuum in the first place.
Doesn't even care about whether the Hamiltonian is integrable.
It definitely does not care about whether the Hamiltonian is integrable or chaotic. In fact, we will apply this formula to both integrable and chaotic systems, and you will see it accurately reproduces. You can do the numerics, accurately reproduces things in the large system size. Yeah.
That goes into the variances.
Yes, I will come to that in a minute. There's actually something that's different between chaos and integrability, which is that the reason I'm emphasizing the averages is this doesn't talk about the variances around the mean. Right? This is the average value that you're getting, right? The actual system at finite n is going to have variances around that. And that this is not calculating. So what we will do is we will find a way of calculating that also for random matrix theories. We'll get a particular answer, and then we'll compare with both integrable and chaotic spin chains. And we will find that we can reproduce using the analytical formulae things for RMTs, but the variance formula we get at RMTs does not match integrable spin chains at all. Right? But the mean formula does. This one does. So that's what I'm going to show you in a second.
So just to go back to the last discussion, at least the ultimate all results suggest that the growth of Lanchos coefficients do connect, at least to.
So I don't think, in my opinion,
Well, that's not chaos for you, but let's say short time chaos.
I don't know if it's even chaos. I'm going to show you an example where you can write down a spin chain that's integrable and has the same short-term dynamics as a theory that you would say is chaotic, but isn't. And so
it won't have Lyapunov exponents.
The connection between Lyapunov exponents chaos is less tight than you'd think. So, for example, there are billiard systems with zero Lyapunov exponent, which nevertheless have mixing dynamics. So you can have mixing dynamics. We'll see that in a minute. So I think, so I'm not completely sure what words to say. Maybe you guys have an opinion. I would say that early time behavior is probably a sign of mixing dynamics. You can have integrable systems, which are sufficiently complicated to show early time mixing dynamics. They're just not chaotic. I mean, there's a difference between chaos and mixing dynamics.
Late time chaos, the criteria for late time chaos and early time.
Okay,
They certainly are different, right?
Oh yeah, so there's
a spectral form factor, or something.
If you like it.
Dyson distribution.
Yeah, I'm comfortable with phrasing it that way, because I think in the community of people who do quantum dynamics and quantum statistical physics, there's actually a lot of controversy about verbiage, which I'm not fully privy to, regarding what is chaos, what is mixing dynamics, what is thermalization, and different people make different kinds of distinctions between these. I'm actually not completely sure about that. For example, there's a person, a very good person by the name of Polkovnikov, who's at PU, who makes the distinction between weak and strong chaos and this and that, and mixing dynamics versus not. These are papers I need to dig into, and I haven't yet. So they have a certain verbiage about this. What seems like, I would say, is that the phenomena that we're talking about, mixing, thermalization, and chaos, are actually somewhat different from each other. Right? Integrable systems can mix. They do, maybe, right? Like a free particle gas can mix, but is not really chaotic in some full sense.
At least I would say one can show that whether or not you have short time chaos as per the Lyapunov group, it's quite different from whether you have Dyson or whether you have.
I am very comfortable with that statement, and everything we would see would be consistent with that. And I'll show some examples of that. So this analysis here, with this format, we'll finish discussing this in a second. But this analysis here, if you give me the density of states of some integrable theory and some chaotic theory, both I can use this formula to compute this density of states. It may well be they both wind up showing the similar kinds of Lanchos coefficients some period of time, and wind up showing similar early time dynamics. And if we wish to call both of those as early time chaos, as evidenced by the Lyapunov exponent, completely comfortable with that with that terminology. That is not necessarily the terminology everybody uses, because there's a certain degree of commitment people have as to what they want to call chaos and not call chaos, etc. But that's just that's really semantics, right? As a point of how the dynamics looks.
But just to say, just like I pointed out yesterday, that the Lyapunov exponent is just an upper bound.
Yes, yeah, it's an upper bound. But I mean, you really have systems which will not show Lyapunov growth,
Right.
show Wigner-Dyson
That's right, like lower,
etc. etc.
Yeah.
So I'm just trying to say they are different.
They are different. And as Harshit pointed out, it is just a fact that, well, it's a fact. What they showed is an upper bound.
Right, that's
Right.
true.
And
So
so
I'm just saying you don't have to rely on the upper bound. You can actually
you
construct.
can calculate it.
Can you, maybe you said this, but is there an example of the other way around? That is an integrable system that has a non-zero Lyapunov index?
That I don't know.
That I don't know, actually.
That I don't know. That's why I was saying in terms of criteria.
I will show an example. Well, we haven't computed the OTOP and the Lyapunov index, but we'll show you that I'll show an example where there's an integrable system that shows the same growth of both the spread, the Lanczos coefficients and the spread complexity in the early part. And so I would assume
But that isn't. I mean. That's an upper bound.
That's an upper bound. So I can't.
So that's what I'm trying to say. You can just use the Lyapunov exponent as the criteria.
Yeah, absolutely. I don't know the answer to this question.
But you still have chaotic systems which have Lyapunov growth, which don't
Show Lyapunov growth.
Yeah. You can have a system which does not have Lyapunov growth but has Wigner-Dyson still.
Yeah, I'm going to show you an example of a billiard system later that has Wigner-Dyson-like statistics, but has definitely no Lyapunov growth.
Okay.
Right. So I will show you that. The other way around, which is what is also being asked just now, do you have an integrable system that does show Lyapunov time growth? I don't know the answer to that question. Indeed, as you guys keep emphasizing, that they have an upper bound, so it doesn't guarantee that what happens for the integrable case. That just has to be studied. Another issue with trying to study integrable systems is that it's like the there's the Anna Karenina thing, all happy families alike, but every unhappy family is unhappy in its own way. So it's like that. All chaotic systems are alike, but every integrable system is integrable in its own stupid way, right? They're just sort of all special and different. They've got symmetries from the other. I think that's what makes it hard to study it as a general class, but I'm not aware of an example. Okay, so let me finish the argument here. Okay, so we have some continuous large and limit, and I'm going to break up the Krylov chain into segments. I've tried to argue that in order to have the limit, you should have constants here, here, here. Again, this is not a formal proof. This is a physicist-style argument, right?
System, you said the variance will end up being different.
We'll see that in a minute. Can we come back to that in a minute? I will demonstrate. So for a Toeplitz matrix of this kind, you can work out what the spectrum is, and you can just read it off from wherever. And then
Type binding.
It's a type binding model. Yeah. So right, see, so the cosines and things like this. And so what you can do is now you take the Large-N limit. Right. So when you take the Large-N limit, well, I know the spectrum here. So then what I do is I do the Large-N limit. I know the density of states is 1 over d, dk, etc. And then you have to sort of assemble all of this back together. So you're trying to reassemble the full density of states from these, but you want to take from here, from here, from here, from here, each of these blocks. There's some contribution to the density of states, right? There's some support on different energies in each of these blocks. So you need to assemble that. And that's what this assembly is doing. And so this takes a little bit of work, and I've not done the work for you here. And that will give you this formula.
It's like a scalar field with a coefficient of x behind the kinetic term, roughly speaking. The kinetic term is sort of b or something, and that's changing it.
Oh, I see. Yeah. So if you were to write down the continuum version, which that's an interesting thing to do, actually. You take the Krylov chain and you turn the continuum model to have things. Yeah.
I mean, is this formula sort of, can you invert it in a sense to obtain the b bars and the
let me explain that. So that's what I'm going to explain now. Okay. So first of all, this is valid to any system with a Large-N limit, need not be chaotic RMT. And let me explain. This is something I manage to confuse myself every time I say it, so we'll see if I succeed this time. there's a way of inverting the integral formula, at least numerically. Occasionally, you can try to do it analytically, and I'll try to explain it. Yeah.
So you had this method too for the thermal states, right?
Yeah.
So can you derive this formula from there?
Yeah. So in the cases where you can derive things in other ways, you can relate them. I'll say more. Hopefully, you'll find it more. So maybe I should give the formal mathematical proof, but I didn't prepare that today, and I'm not going to try to hazard to do the details right now. What I will do in a moment is I will give you an argument for RMTs where you can derive this formula through other means, saddle point techniques. And then I'll derive a formula for variances and covariances, also using saddle point techniques. So hopefully that'll add some confidence that there's two ways of getting it. Okay, so now let me talk about the strategy for solving this. Okay, this is what you were asking. So notice if I look at the numerator is non-zero when a minus 2b is less than e is less than a plus 2b. Okay, so I'm going to assume that the support of the energy in the integrand shrinks monotonically as x increases. This is related to the various. So this requires something. It requires that b prime is less than 0, the derivative, and a prime is less than minus 2b prime. What I really should do is I should tell you if the theory satisfies certain conditions, this will be true, but I can't tell you what those conditions are. This seems like something that you should be able to derive on the basis of blah, 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 reflection, positivity, something, but I can't do it. So we'll tell you that in every example that we worked on, this was the case. So, okay, I'm going to accept it. So then you assume that. And then, if you do that, then there's a recursive procedure you can do. What you can do is you first start off with the smallest support.
And it's effectively a WKB approximation for this.
It will in the RMT, it effectively is a WKB. Let's just see that we will see it as a WKB approximation in 2 minutes when we do the RMT example. We'll do it as a WKB. Exactly. So all this averaging and stuff, the same thing as looking at saddle points. So you can write down an effective action for this, and then take some saddle point. We'll come back to that. So anyway, and so do I really want to go through this? So let's see. So you can. So in particular, if you consider theories for which this a is 0, then you can write down some more analytical thing. You can do some Laplace transforms, and you can sort of deconvolve by hand in some cases. Do you want me to go through this? Let me just skip it. And if you feel the spirit moves you, you just ask me, and I will come back to it slightly to see. So anyway, so there's some numerical procedure and some special cases where a is 0, you can actually deconvolve and things like this. But in general, what you do is you first go to the case where the support is very, very narrow. So therefore, there's only one coefficient to read out. Oh, once you know that coefficient, then you have to open it a bit more, right? By changing so you look at the biggest x and then you keep going like that. So there's a numerical procedure where you start with the smallest support and then you increase the support. So you can read off the smallest thing. So slightly indirect, and in some special case, you can invert by doing some Laplace transform technique. Okay, so now perhaps this is more interesting.
I mean, the denominators are something like E minus B.
Yes.
Square root of E minus.
Yeah, you're noticing the WKB because of this, right? This looks like the kind of formula that is going to show up in WKB, right? Indeed. Exactly.
I think if I would have solved my continuum scalar field, WKB would get exactly.
Yes. So let's do the matrix model version of it. So interesting for us is to look at random matrix theories, because of course random matrix theories appear ubiquitously as models of chaotic systems, and we use them for all kinds of complex interacting, as models of many, many kinds of complex interacting systems. So by random matrix theory, I'm going to mean I draw matrices from some distribution where I have e to the minus beta n over 4 beta some parameter, and I have the trace of some potential, and this is the Hamiltonian. So the potential we're going to take to be some polynomial in the Hamiltonian, and the standard ensembles that people pick are the GUE, the unitary ensemble, or orthogonal ensemble, and the symplectic ensemble. There are other kinds of more exotic ensembles you can also pick. I think we'll briefly talk about those more exotic examples later, but these are the standard ones. Okay, so suppose I give you one of these standard things. Over decades, there has been a lot of beautiful work showing that you can write down a theory of the eigenvalues, namely, you can write down the probability distribution of the eigenvalues for such draws or random matrices. And you will recall that the way that works is there's a van der Waals determinant, right? So you have some lambda I minus lambda j to the power beta. And then you have e to the minus beta, all of this with the potential now written in terms of a diagonalized matrix of eigenvalues. So that's the distribution of eigenvalues. And there's a nice formula that you can use to invert between the potential and the density of states, or the density of eigenvalues. And you have to do, say, v prime of omega is going to be the integral dE of the density of states divided by omega minus e. There's some principal value thing you have to do. So these are all ancient, things that are there in standard random matrix textbooks, even. So the question is, can you write down a probability distribution for the Longshore spectrum? And the answer is yes, actually. So in one this paper, we show how to derive this, and so actually I should say, in 2002 or 3 or something like this, there was a paper by two mathematicians, Dumitrescu and Edelman, that did this for Gaussian random matrix theories. And what we're basically doing is generalizing their work to do a random matrix theory with arbitrary potential. And the net answer turns out to be like this. After some work, there's a distribution in which instead of the van der Waals determinant, you will get here a product on these, in the Longshore coefficients, the diagonal ones, which we called A, and the off-diagonal ones that we call B's. So there's something here that involves the off-diagonal, the B's in this way, that provides a measure. And then you get here this thing, which involves the trace of V on the Hamiltonian. And now you should understand the Hamiltonian as being this tri-diagonal thing. So of course, when you take powers, it mixes the A's and B's in some particular way, which you can calculate, and you can write this out. That is the distribution that you can show. Right?
And here you're taking both the initial state as well as the matrix, Hamiltonian.
It's a random matrix. So it's a random matrix. Any initial state matters.
Oh, it
will be fine. So that is another reason why random matrix theories are convenient, because anything will do. Helpful. Okay. Yes. I'm wondering if I want to contradict myself. What happens if I pick a given draw of random matrix? You see, well, okay, now this is the distribution of eigenvalues over all the matrices. Yeah, any state will do. Any state will do. Yeah. I was about to say, well, if I pick a given random matrix, of course I could pick another, but you're changing them around.
Okay. Unitary and any state.
Yeah. So one thing when you're doing, if you're trying to do it numerically, you have to pay a little bit of care. Don't pick an initial state that happens to be an energy eigenstate of one of your matrices, because then it'll be an issue, etc. So there's some care taken there, because you're taking finite matrices and working with them a certain fraction. So when it actually calculating the dynamics. Okay. Anyway, so you can indeed, as you observe, so think about this as an effective action, and write this as e to the minus s effective, where this is simply the log of the distribution. And now you can observe that if you mess with it a bit, because there's n here, and there's a product of many terms here, this is going to be sharply peaked at large n. So now we can use saddle point techniques, WKB methods. So what do you guess?
In that sense, similar to you obtain W sine of omega s.
Exactly. Yeah. Same techniques that have always been used in matrix models, except now being done instead of using the diagonalized matrices, using the tri-diagonal matrices. So, yeah. So if you do that, you can show, the first thing you can show is that the same integral equation we derived above, relating the density of states in Longshore's spectrum, remains true. And the second thing you can show is that there are these equations for the covariances. So this is AI plus delta. Let me just show you the details of how that's done. So what do? I'm just emphasizing that there's an actual calculation you can do if you feel like it, which is you take that exponent, you take some derivatives, and you have to find the saddle point. The saddle point equation turns out to be something like this. You'll recognize the presence of the square root, there's a potential, and then you have to try to solve this. And the covariances is doing a similar way. If you expand that effective action in powers around the saddle, then there'll be some quadratic terms And this is those things that we. Okay, so you're doing basically, that's just to say you're doing the same thing that you would do, except now you have to worry about A's and B's. And so you get these equations for the covariances.
Variance is all suppressed in 1 by n for all values of smaller. Meaning that, I mean, of course, when n is order 1, and a capital N going to n,
Yeah.
I don't believe them. I believe that it's also true when scales with capital N, but little n scales with capital N. But
I mean, I'm looking at this formula, and let's see. This is a phase. This is an integral up to 2 pi. So it's all in the lambda, whether there's a competition with the n. Lambda looks like this. Lambda looks like this. There's some b's. These are typically, order 1 type numbers.
so you're saying the variances are all small throughout this.
Looking that way to me. Yeah. Looking that way to me.
And as little n approaches capital N, something goes up.
Yeah, that's what I was wondering.
Yeah. So
Is B is equal to 0, right?
B is going to 0.
So yeah, I guess from that point of view, even if you have an order 1 fluctuation, that becomes.
Yes.
Okay.
Yeah. So I can't. What I don't know, and which I can't directly comment upon, is exactly what statement I would make near the spectral edge, near the 0 and the end, because there's some saddle point technique being done here, but actually, the edges, you have to do something to make sure the boundary conditions fix. I'm a little bit confused as to what happens at the edges, actually. Yes. Okay, so now I'm going to do one more method, and then we'll start to do some applications. So this method is also very beautiful, and for people who are familiar with matrix models, it will also evoke some memories, if you like. So let's suppose you write your.
DTP has an ML Mehta memorial lecture.
What's that?
Department of Theoretical Physics has an ML Mehta memorial lecture.
He is smiling down on me right now. Yeah, Professor Mehta would be definitely happy. Okay, great. So I take the state psi of t, and remember, our method has been to expand this in a Krylov basis like this. Okay. So now, but normally that's not what we do. We expand it in the energy basis. So how do I expand the energy basis? Well, I have to. We're taking some continuum limit again. So there's a dE spectral density. Well, okay, I suppose we could make the spectral density delta functions too if we felt like it. This is the initial state written in the energy basis. And we have the usual, weighting as time flows. I should say, so myself, I learned these things basically from work done with Pavel and Pavel Saputa, Joan Simon, and another paper I wrote with Johanna Edmenger, Jonathan Karl, Ratan Das, and Herman Verlinde. But I should say that actually in those papers, the others may have learned these things differently, but I learned many of these things from some very nice papers by Wolfgang Muck, this paper, and Muck and Yang. And they're very nice papers on this Krylov stuff that use these methods, or some of these methods anyway. And I learned some of the ideas from there. And there's actually an older paper by Arjun Kar, Jamie Sully, I think Moshe Rosali and everything, random matrices and this and the other, where some of these things are revealed, which I was not aware of that at all, but it's very interesting. Okay, so you can write this in the energy basis in this way. So now recall, what have we said so far? The first thing we said was you can compute the Krylov basis in these ANs and BNs by this recursion method of Langshaw's. Now, so if you just start with the first state and you just start doing this again and again and again, notice every time you're acting with the Hamiltonian a few times and the subtracting and everything. So what you're going to wind up with is a polynomial in the Hamiltonian. Basically, it's like h minus an is some number, then you act with it again, then you subtract something, etc. That's going to give you a polynomial. So you know that the Krylov basis element is going to be obtained by the action of some kind of polynomial in the Hamiltonian on the original state. Now, remember, that recursion led to a formula which said h acting on the nth Krylov basis element would either keep you in the same place or move you forward, move you back, tight binding kind of effects. Now, if I translate it into this picture with these polynomials, that means the Hamiltonian acting on the polynomial can either keep you in the same polynomial with some coefficient, or take you to the previous polynomial, or take you to the next polynomial. So those of you who are friends with orthogonal polynomials, classical orthogonal polynomials, will recognize this kind of thing. This is the kind of three-term recursion formula that comes up again and again and again in the theory of classical orthogonal polynomials. Laguerre polynomials, Legendre polynomials, all of these things satisfy these kinds of three-term identities. So this looks just like that, except these ANs, BNs, and everything. Of course, what those coefficients are determines which polynomials you have. Okay. So in this work with Johanna and Herman and Jonathan and everything, I'll tell you later, a beautiful thing happens for 3D gravity in this way. Okay. So now I'm going to consider the coefficient Cn of E, which is the support of the nth basis Krylov basis element on the energy basis, on the energy element basis element E. So so you take this definition, you plug it into these things, you mess around with the definition of the Krylov basis like this, right? With all of this and a little bit of algebra, and you will discover that Cn of E is the initial state phi naught of E, this coefficient, that is the initial support on E, because and times this some polynomial. This is basically the same polynomial written as H because it's written in terms of the energy as opposed to the Hamiltonian. So you get some polynomial built of degree n, actually, of degree n. So this is support of the nth element, is the degree n polynomial built from Langström's coefficients. Now comes the final thing. You require.
Really sorry, so Tn of E is this overlap.
Is the overlap
with some energy eigenstate.
Correct. So then what you want to do is, I know psi of t written in the energy basis is like this. Psi of t written in the Krylov basis is like this. So now what we're trying to do is we're trying to read off E overlap Kn. So that's a little bit of algebra. You got to do the overlaps, do some this, that, and the other, and then you can also use this formula. And so there's a little bit of algebra to be done. We can do that if you like, but it's well, we'll have to make a new page and mess with it. Okay, so the next step is to recognize that the Krylov basis elements were constructed.
So it has very high support at high energies.
Correct. So what is going to happen? Is, well, so what precisely is going to happen is bigger you make n. So so it's a polynomial, but the polynomial is going to have, depending upon what the n is, it has more and more support in high energies.
Yeah.
So there is a sense in which the flow to higher Krylov basis elements is also a flow towards more support on the higher energies. It's not precisely one-to-one, that relationship. It's a different presentation of the dynamics that mixes all the energy eigenstates in a way that's convenient for describing how the dynamics works. So it's a different way of thinking about the dynamics. But there is some relationship, as well there should be. Okay. There's another interesting thing that I would like to understand that I haven't really understood, which is that there is some sense in which the higher basis elements, Kn for large n, should be more structurally complex. This goes back to the comments I made on the first day, possibly when some of the audience members were not there, about how black hole microstates should be structurally complex. There's something structurally complex about these big ones, but then you have to come up with an understanding of what structural complexity is. There was at some conference of the CMSA at Harvard earlier in the fall, in which there's this new notion of something called O minimality in mathematics, which concerns some quantification of the the mathematicians are using the words that it's a quantification of how complex a function is structurally. And there's some interesting new developments. So apparently I got invited to speak there for this reason, and there was some discussion about this, but I haven't followed up. So the higher HNs are somehow more structurally complex. I believe that must have some overlap with ideas from the thermalization hypothesis, right? Because that's somehow talking about the structural complexity of energy eigenstates and everything. So there's a whole bunch of connections there, which I'm not going to be able to tell you more about.
So the spectrum of E is like this Wiener kind of distribution, right? Bounded from both above and below.
Well, if it's a semicircle, if it's random matrix, but we don't have to talk about random matrices here.
But here you're not talking about random matrices?
No, this is a general statement.
Oh. But in the case that it was random matrices,
yes.
You're trying to understand what distribution is moving. up in energy and down in energy. I mean,
Yeah.
the typical state will be sort of in the middle of the spectrum. Why do higher line coefficients give higher rather than lower? So I guess by very.
Oh,
It just depends on
it depends how you start.
Yeah, to see it. If you put the spectrum, like starting from positive energy, then it will go to the
Yeah.
other edge.
It depends where you start. You start in the middle and
There
spread
is a
out the
weight
direction.
right?
I thought you
So
started with a random state.
normalize this.
What's that?
I thought you were starting with a random state. So we start with just some random state that's sort of in the middle of the spectrum, right?
Well, we spread out. We'll have
Right.
support.
So it's spread out both ways. So this seems to be saying that it goes higher and higher.
Yeah.
That's what's worrying.
Yeah. Okay. So, whether it goes well, I can't tell you whether it goes higher and higher. Usually in the states that we've been thinking about, you're talking about some relatively smooth. Well, okay, when I say that it goes higher and higher, you're talking about some smooth initial state and a spin chain, and the smooth initial chain develops more and more decorations. And so the decorations look more and more as if there's some support.
So maybe this E is roughly E minus middle of E.
Yeah, exactly.
Perhaps. Yeah. Perhaps. Can't quite answer that question actually. Anyhow, putting that on the stack for later discussion, because that's an interesting question. Also, these are points about the structure of the wave function, whether you're moving in where in energy. I actually don't fully understand. That's something we've only started thinking about in the recent past. So I will not be able to fully satisfy that.
It's also the case that you are normalizing your HNs
Yeah.
in ways which have a density of states.
Oh yeah, I'm going to tell you that right now. Yeah.
So what I'm wondering is, you might conclude that HN is growing with energy, but if rho is falling, with
Yeah.
energy, the net import of that will still be that you're focusing your energy.
That could be the case. Yeah. For RMT like things, that could well be the case. Yeah, absolutely. Well, that could be the case. Again, this is not something. Let's shelve that. These are good questions. And we'll make good material for a discussion at the end today or on the next lecture. So let's definitely talk about it. And it's points I don't fully understand. Okay, so if we so the next thing to put in is that these Krylov basis elements are supposed to be orthogonal. So you can just evaluate. You've written the Krylov basis elements in terms of these polynomials, evaluate it, and you see, as you just said, that the orthogonality condition is that you integrate dE, density of states, and initial state too. Now, what you put in as the initial state matters. Right? Yeah. So what's very interesting is that there's some infinite families of orthogonal polynomials being considered here, which are indexed by the density of states of the different theories you could write down, and by the initial state. So the usual orthogonal polynomials, they're orthogonal in some very particular measure, this measure or that measure, or this is one, or something like that. Often it's one, not always one. Sometimes you have an exponential there, things like this. But so this is a state and density of states dependent families of orthogonal polynomials. So this is again at this conference I was at, the math people were going on about something that sort of resembled this, about families of orthogonal polynomials and blah 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 with some exotic measures in front of things. So there's some connection there, which I would like to follow up. Anyway.
The random matrix theory literature, people used to consider these orthogonal polynomials for the potential of the random.
Yes. So
here it's for the density.
Yeah.
And do you understand?
I don't understand the relationship between the orthogonal polynomials that somehow involve the potential. Of course, the density is related to the potential, but the density is related to the potential through this integral formula. So there's some intriguing connection there with matrix models. This is something that I've just started thinking about with the same crowd as the Erdmenger and Verlinde and things like this. So we just started. But I think there's some very intriguing connection there with the standard theory of matrix models and what the relationship potentials of the potentials there should be. The obvious way to do this, to develop some intuition for the connection, is to just do this for matrix models and try to see what would be the polynomials, what's the measure, what's the relationship, how does it relate to the initial state, this, that, and the other. But we haven't done this. So, but I think it's an interesting direction for the future. There's a sense in which what this is doing, if you think about that formula for the mean A and B, and this kind of formula using orthogonal polynomials, that somehow what it's sort of doing is it's turning any theory into something that looks like an RMT in terms of many of the formulae you write down. It's not an RMT necessarily, if it's integrable or something. It need not be an RMT. It need not have Wigner Dyson statistics, we need not have level repulsion, but there are various aspects of the dynamics of any system in the large system size limit that have an RMT-like form, right? But all of that to be investigated is just an idea or a direction feature.
I really want to say something.
Yeah, do it.
When we quantize JT in TS, we found all the eigenvariant states in some stuff there. And the natural norm which comes out is exactly this.
Excellent.
With phi naught of E being supported democratically. So
very interesting.
Very interesting for me that get this kind of thing.
We should talk about that.
There's a lot of confusion about what is a natural norm, in the de Sitter context, but there's a sense in which this was the most.
Okay, I would love to hear more about that and to talk about that.
One or both times fine.
Fine.
So I would love to, because he said it was a democratically supported the whole thing or something. I would love to talk more about that. So we won't get to this today, but in the next lecture, if I don't talk about black hole microstates, and I instead talk about this recent paper we had with Herman, there we're talking about 3D gravity using some density of states written down by Maloney, Witten, Keller, and Maxwell Tudiachi. And we also get some formulae that are like this, and I think there's some interesting polynomials that arise into. So basically, we're trying to compute directly in the 3D quantum gravity, some measure of the spreading of the quantum state. Because supposedly, if you give me the density of states, I'm supposed to be able to do this, right? So if you give me the density of states, someone else calculated, and I should be able to do it. So things like this happen there too, and there may be some connection there because those things, that density of states is written down for the near extremal 3D gravity, and the near extreme 3D gravity kind of more or less reduces to JT with maybe some little bit of fuss and mess. So there may be some interesting connection. I would love to understand better what you guys have said. Okay, anyhow, so if I take all of this and I plug it into that formula for the spread complexity, again, this is like a page, half a page of algebra. We can do it if you like. You will get a formula, an actual integral formula for the spread complexity, which looks like this. Isn't this nice, right? I mean, so what you do is you have some, basically it's like a 2-point function, Fourier transform of a 2-point function in this way. So this is the Fourier bit, changing energies to time. You have a density correlator, basically, right? At E and E prime. You have the initial support of those two energies, because that modifies it. The effective density of states is actually the density of states times the support you have there squared. So it's a notion, a state-dependent notion of effective density of states that is coming out. And then you get this thing that I'll call a complexity kernel that is built out of these orthogonal polynomials. And those orthogonal polynomials are holding in them, in some processed manner, all the information about these Langshauss coefficients and the spectrum and all of that is coming. So that's a beautiful formula, I think, because if you tell me the real density of states, you just write this down. That's a matter of doing the integral. And there are some cases where you can do it. Other cases you do it numerically. And so I find this formula nice. Okay. So, good. So let's do some applications. Okay. So the first application, this is from my original paper on this with Javier Magan, Pavel Saputa, and Austin Wu, is let's say, the first thing you should do is when you get some new formula is you need to work at some examples. So, and then you should also compare the what you worked out in cases where some known answers existed, either for the same quantity or for different quantities, to compare the physics and understand. If you're saying compare chaotic and integrable theories, how to standard measure. So we'll just basically do that for a bit. And in the end, we will come to some application to quantum gravity that will be sort of novel. So, okay, so for the thermofield double state in SYK, or for random matrix models. Right? So for the SYK thing, we're building the TFD. Remember we said you can do this formula where if you compute the thermofield double state, then the survival amplitude is related to the analytically continued partition sum. So, well, SYK is a theory where people have done work on calculating the partition sum. You can use that, and RMTs is described. And we're doing, so in the random matrix models, we're using generic initial states. And SYK, it's a thermofield double. you compute the spread complexity, and you can do things. Do I need to review what the SYK model is for this crowd? This model where you have n Majorana fermions multiplied each other, and you have some coefficients. The coefficients.
The whole point of fine print is that you don't have to look at it.
So the reason why one of the reasons why I really like giving talks in this way is that you can put the stuff there, and then you can just sort of expand it and everything. It's so nice. Eh? So partly I did this for the joy of expanding it. You can just see it. So cool. What's that?
What's the
This is good notes on the. So I learned this thing from during the pandemic. I was struggling to give lectures, and Tomonori Ugajin, who was a postdoc at the time, was using this. It's like magic. You know, you got so much collaboration done because you can do this kind of thing. So
Can you add footnotes?
oh yeah. Sure, you want to see? So good. It's so good. Okay. You can't do all the fancy stuff on PowerPoint, but who wants to do this part? The fancy stuff on PowerPoint. It's so much more cool. Okay, yeah. So just to remind you, and I'm doing this only because I feel like it's nice to expand it, as we said. Anyway, SYK model is a bunch of Majorana fermions. You multiply by some couplings. The couplings are real IID random variables, and there's some definitions of coefficients. We'll come back to that some more because we'll need that later when we start talking about wormhole length and everything. Okay, so what happens? You compute this spread complexity, and you get this famous initial quadratic growth in both of those cases. The quadratic growth changes into a linear ramp. The linear ramp, so we'll call this the ramp. It persists up to some exponential time and arrives at a peak. We'll call this the peak. Then there's a downward slope, and then the slope ends up in a plateau, and the plateau will be exponentially high and reflects the size of the Hilbert space. It's going to be, if it's evenly spread out about the Hilbert space, accessible Hilbert space, it'll be like it'll give you half the Hilbert space size, will be the height.
And what is quadratic? Because in time t, you've reached n equals t, and then you're summing over n, so that's n squared. It's roughly that. I'm trying to understand intuitively why you should expect quadratic growth. In time t, have you reached the tth Lankos state? And then that is sum over.
Yeah, okay, so it's the ballistic motion.
Part of the linear part of the complexity, right?
Is that?
Because this is like the expectation value of the position of it.
Yeah.
C of t is just the expectation value of the.
So this quadratic growth is faster than that. And then what happens is that the linear ramp is this ballistic motion.
Sorry, I was thinking if you reach the nth Lankos state after time n, then your complexity will be n squared.
No.
Because
No, because it's a sum on n of n. It's going to be the average position. So if you are,
it's not. You divide by something.
No, it's a probability. It's a Pn is a probability.
Divided,
It's a probability. So the quadratic thing that happens because of some universal fact about what the Langshaw's coefficients are like. There's a sort of SL2R type. There's a form they have which is the same as the form you get for a particle on SL2R. Or a particular version of that, which is what gives rise to this. Would you agree with that?
Yeah, that's right. I mean, the Langshaw's coefficients for very small values of n grow linearly with n. This is the hypothesis of part of it. That's what gives this quadratic. Then they almost become constants.
And that gives this part.
That's this linear part. I'm not actually sure about this peak and stuff.
Yeah, the peak and stuff, that's where it starts to come down.
That's
where, so this is a long way away, right? This is exponential time. So what happens is that the whole order one part of it involves first the growing Langshaw's coefficients, which lead to this quadratic growth, this thing that everybody that you mentioned, Parker et al. Mentioned, and suggests is a sign of chaos. Well, it's certainly a sign of something. It gives you a bound the up and up and everything. And then you get constantly coefficients, which lead to this linear growth. I'll tell you what the phenomenon is on the chain in a second that leads to that. And then eventually, for any finite dimensional Hilbert space, if it's an infinite dimensional Hilbert space, this can go on forever like this. But if it's a finite dimensional Hilbert space, so you know secretly there's some discreteness in it, there's some boundedness of the energies and stuff like this, what will happen, and that will be the key later for our wormhole saturation stuff and everything, that you know that it's actually a discrete spectrum that comes out from the density correlator. Then what will happen is it will peak and then come back. The Langshaw's coefficients have to come back down to zero because when you get to the end of the chain in the microcanonical ensemble, there's nowhere to go. So the Lanczos coefficients have to vanish when you get to the end. And so that means that they have to come back down. If you try to, by the way, when you do the gravity application, the magic of these methods is that if you try to compute that descent of the Lanczos coefficients to zero in gravity, these are non-perturbative effects. They go as e to the -1/g_Newton. So they're very, very small effects. Wormholes, all this stuff needs to be used. But on the field theory side, you don't need to do that. We have, in fact, displayed a closed form integral formula for calculating it in terms of the density of states. No wormholes involved. You can just calculate it, and it will go back down. So we'll see that later.
Field theory means like in matrix.
Yeah. So in this case, the matrix model or the SYK everything, it's not a straightforward. It's not a continuum field theory in that case. So since the question was asked here about about the linear part, what you were saying, Shiraz, what happens is initially, the state is initially completely localized here. So then what happens is that this thing kind of moves out, the peak moves out and leaves some probability behind like that. Initially, when it's doing that, you wind up getting this quadratic growth. And that is related to it turns out, in many cases, for reasons I cannot fully articulate, you will, or I can't tell, okay, you get this increasing Lanczos coefficients. That's what drives that, right? So in other words, what happens is that you start off in the initial state. The hopping from the initial part to the first thing is slower. Well, the next one, 1 to 2 is faster than 0 to 1. 2 to 3 is faster than 1 to 2. So it gets faster and faster and faster. The speed increases on this chain, and that causes this quadratic growth. If you were to ask, what is the deeper fact about the theory that leads to this quadratic? I don't quite know what that would be in terms of some deeper statement about the theory. I don't know, Onkar, if you know.
I don't know about the quadratic part. I thought that if you did this in the thermal state, you get exponential growth.
In the thermal state, you get exponential growth.
That's, you could imagine, I don't know, I mean, you might want to interpret that holographically as like this particle falling in.
Okay. You can interpret that. That's the Joan and Pavel, or this stuff that you did. Yeah. Whoever did.
Yeah.
These
like exponentials are usually
that's like a particle falling into the ADS space, and you see the rapid fall and everything. So the thermal states, there's that.
It's not just that in the SYK, once you're past, just a little bit past the edge, you have exponential growth in number of states, e to the square. I'm just wondering, many more states at the next level and the next level.
Or maybe it's that.
And then I was just wondering, I can't directly correlate it.
In SYK, I thought it was going to be if you start with the fermion, then in the Hamiltonian will make 3 and then 9. That's right.
So that's consistent with what he said.
That's
No, it's more precise version of what you were saying, but I was thinking in terms of states, here, because the states grow very rapidly, right? Exponentially rapidly. So I'm just wondering whether that
it could be.
I can't relate it directly to quadratic.
Okay, it could be. It could be. I don't have a good answer to that. And it's a good question, because the quadratic thing is pretty universal. It appears in many places. It'd be good to have a account of that says, well, look, if the density of states increases in the following way, and the state is not generic, it will go like this. I can't quite give you that, because we mostly focused on the very, very late times for reasons that will become apparent later, because we were interested in whether or not these wormholes saturate everything. We'll come to that. What I can tell you a bit more about is about the linear ramp.
I mean, it should be related to the operator.
Absolutely. Absolutely, right? So those two statements have to be related. Yeah. And as another thing I should probably have talked about or prepared, but I didn't, is there's some relationship between, if you do this for something that is an ADS dual, the momentum of the particle falling in is related to the rate of growth of the complexity in a given way. And that's why there's this interesting relationship within thermal states and exponential falling in, things like this. So maybe I'll try to prepare that for the next. This is work by Onkar has worked on this kind of thing in this group. There's also work by Joan Simon and Pavel Saputa on this kind of thing. Okay, so what basically happens is that when you pass this initial bit, this little bump, this is supposed to be the Krylov direction of the chain, and I've sort of drawn it with a continuum, some large n limit. This thing begins to move out ballistically. And so that's this part. But in any finite dimensional Hilbert space, right, if you're in the microcanonical ensemble and there's an underlying discreteness to the spectrum, you eventually have to reach the end of the Hilbert space. And when you do, this thing bounces back. And as it goes this way, it drops probability, leaves behind some probability. So it sloshes back and then evens the thing out. So this is the linear ramp up to here, and then the sloshing back leads to this. Okay. So, and you can see that the peak and the slope are determined by the universality classes of the theory. So, for example, if you look for an RMT at the GUE, GOE, or GSE, the way this looks is different. This is my artist's impression, so to say. For the GUE, it's sort of it comes in kind of sharply and then kind of goes this way. The GOE slowly goes down like that, and the GSE oscillates around what the plateau will be. So kind of robustly, depending on the class, it's like that. We can sort of drill down a little bit more on that.
Yes, it's symplectic.
Symplectic. So here we can drill down a little bit more. This is all for GUE. So what I'm doing here is, this is for different temperatures, the different lines. What we're going to do is the dark lines are all draws from a GUE. You see, and you get this peak and sort of goes down here and kind of runs into the plateau and then sort of stabilizes. The light hues are a theory that has the same density of states, but doesn't have the spectral rigidity. If you're doing RMTs, you can build Hamiltonians like that very easily. The way you do it is you simply draw eigenvalues randomly in the Wigner semicircle. You make up a matrix like that. So you make up a matrix which has eigenvalues drawn randomly in the Wigner semicircle. So then you don't have spectral rigidity, right? You're just drawing the eigenvalues randomly. You just build a big matrix like this. And then to make it look random, if you like, pick some random unitary and rotate it, and it would look like a random matrix. And it'll have the same density of states as a random matrix theory, but doesn't have spectral rigidity. So that's there's other. If you want to take any Hamiltonian and build a different. What do you mean by spectral rigidity? So there's a density. There's a eigenvalue repulsion.
Okay.
So there's a density correlator. As you know, there's the sine kernel, this, that together. So that's what I'm referring. So rigidity, because there's a sort of it doesn't get that close. It's sort of rigid in a certain way. So if you incidentally suppose you have some other kind of Hamiltonian, not RMT, and it has some density of states and also has spectral correlations, and you want to build some other Hamiltonian which has the same density of states but doesn't have the correlations. There are techniques for doing this. So there are ways of doing this. But we didn't need to use them.
You can build designer Hamiltonians which have
with Poisson spectra that have whatever density of states you want.
Yeah, with Poisson, but then if you wanted to incorporate the 2-point rho, you could do that.
You could probably do that. Yeah, I haven't looked carefully into that, but I'm sure, right? I mean, you'll have what you will want to do is you will want to build some maximum entropy ensemble that has the correct correlators built in as constraints, and then draw from that. So this will definitely be possible. And so that's a nice way of checking out which features of a theory matter. So, from the spectral point of view, the light lines are integrable theories, quote unquote, because they have Poisson spectra. So, if you take that quick and dirty diagnostic, Wigner-Dyson is chaotic and Poisson is integrable. Then this is integrable, it's chaotic. They all have quadratic growth in the beginning. This is why I was referring to this. And they have this linear thing. The difference is that if you look at the ones that are Poisson-like, they don't have the peak and the slope down. Those are characteristic features of having repulsion between eigenvalues, rather than sort of smoothly goes into the plateau and stops there. So I just want to draw an analogy that we've seen this before. We should expect this, right? Because I'm going to draw an analogy. So here we have a ramp, a peak, a slope, and a plateau. These are an analogy with the spectral form factor, slope, dip, ramp, and plateau. They are an analogy. In particular, you can play the same game with a spectral form factor. You can take an RMT, compute the spectral form factor, and you get this, dip, ramp, plateau, all that kind of stuff. But if you wipe out the eigenvalue repulsion, just basically build a Hamiltonian without that, like this thing will come down and smoothly go to the plateau, no dip and ramp. So we know this will happen. This is a different incarnation of that. I'm just trying to say that the early behavior is no sign of chaos from the Wigner-Dyson type of definition. Right? It's a different kind of diagnostic.
For the spread complexity, do you have a picture like the one you had previously where the particle moves and then sloshes back?
Yeah.
For the integrable case, like why it doesn't have the speed?
I should have drawn that here, but anyhow, what happens is that as it's moving forward, it drops a lot of probability everywhere. Also, stuff gets stuck. There are bits of it that get stuck in different bits of the chain. You lose things in different bits of the chain. You'll see why in a second.
So it's zero by the time it hits the edge.
Well, it's uniform.
It's already uniform.
It's already kind of uniform.
Sorry, if you're confused about something, if you just go to that next slide.
Yeah.
I thought if you had something where you just had Poisson, so move Wigner-Dyson statistics, that the plateau would go away because there you're seeing the nearest neighbor repulsion.
Depends what you take. No.
Is that not true?
No, that's not true. That's not true.
The ramp is a signature.
The ramp is a signature.
Even though you don't have any your Poisson statistics,
Absolutely.
you get a plateau.
Absolutely. Actually, you can do many things. There's another example where, so this is some paper wrote once with Gabor, Sarosi, and Bartek Czech. So here's an example of a theory that is a free theory, yeah? Actually, no, in that case, there'll be a ramp, but the ramp is logarithmic. Okay, well, I was...
I see.
Yeah. So if you have Poisson statistics, you can definitely get this. Okay, so in this example, let me give you an example, which is definitely not chaotic in the usual sense, but it has a weird spectrum, so it'll sort of kind of generate a ramp, but it'll also go to the plateau. So consider the kind of D1, D5 string kind of system, where you have some very long string, except it's been fractionated into multiple pieces, right? So on each of these strands, multi-wound bits of strands, the momentum is quantized in units of one of the total length. So in the large n limit, your spectrum consists of all rational numbers, right? Very strange, and it's maybe some degeneracy depending on how many things there are. So what you can do is you can construct this theory, right? And then go ahead and just do the spectral form factor for it. And what you'll find is it has a beautiful dip. It precisely reproduces the BTZ black hole exactly, practically, in that theory, if you take it from a state, all the way to the dip. But then the ramp is going to get messed up because you don't have spectral repulsion.
That will get messed up.
But you do have sort of gaps in every bit of the spectrum because it's rational numbers. It isn't really Poisson-like. So what you get is a logarithmic ramp. I view that as a step between somehow this and this. You get a logarithmic ramp, but it still goes to a plateau because the plateau is determined by how spread out you are on the Hilbert space. For the same reason as this, actually. Okay. Okay, how am I doing on time? So I'll just go a little bit further.
Yeah.
Yeah, and okay, so all right. So next, what we should try to do to build some understanding of the measure is to work out how it works for chaotic and integrable spin chains. It's a subject very well studied. So we're going to take 4 examples of such chains. We got these from a paper by Banyuls et al. And so she wrote. This is a paper she wrote with Sirac and other people in the field. There's another nice paper by Eliezer Rabinovici, Shir, Sonner, Sanchez Garrido. Nice work from them. And these are 2 examples of integrable spin chains. So this is on a chain you've got X, Y's, and Z's, Pauli matrices, stuff like this. And here are 2 examples of chaotic spin chains. This thing has some one-site disorder, some details. So exactly why these are integrable and chaotic, there are entire papers written on the subject, but the handy-dandy version of that is that you can just compute their spectra. And you'll find that the integrable ones look like they've got Poisson statistics, and the chaotic ones look like they have Wigner-Dyson statistics. So that measure of integrability and chaos. So what I'm going to do is I'm going to see, do our formulae work? Because in this case, we can just work out everything by hand anyway, so we can compare. So let's look at the Lang's coefficients. One thing is that the spin chains we're going to work with are finite. up to the limit of our numerical ability and our laptops. So this also means that there's some finite dimensional Hilbert space of a few thousand big or something like this. So to compare with the analytical results, we're going to use this integral formulae and things like this. This is where we need some averaging, but there's no random matrix going on here, so we can't average over Hamiltonian because we don't have random Hamiltonians. So the averaging we're doing is over small blocks of the spin chain. So in this case, there's no actual origin limit, so I can't tell you that there's a small block relative, that there's some size that's going to 0 relative to the thing, but it's I forget. You pick some small order 1 block to average over, and then you check that your results are relatively invariant to the size of the block in the usual way. But I don't actually remember the detail of what the averaging was. So here we go. So in this picture,
what are you going to compare?
So we're going to numerically compute the Long-Shor's coefficients using the recursion algorithm, and then we're going to use this integral formula that we had in terms of the density of states.
Yeah.
This is checking. Since I didn't show you a proof,
Yeah.
I gave you an argument. We should check that it worked.
The state is random.
This is a random state that we're starting with. Yeah. So here's what you find. So here are the 2 chaotic models. Here are the 2 integrable models. The black lines here are supposed to be the prediction of the mean, local mean of the Long-Shor's coefficients. These are A coefficients, these are B coefficients, with the same density of states of the theory. And the colored things are actual numerical computation. Notice there's a beautiful match down the middle of this. Right? So the next thing you can do is there's a RMT. Remember from the WKV approximation, for the saddle point approximation, we read off covariances and variances of the A's and B of the Long-Shor's spectrum. So we can compare those two because we can compute the covariances here. You can already see that the integrable models have some bigger spread around the mean. So now,
so sorry.
Sure.
So what were the blue and orange?
Yes, so the blues are the diagonal Long-Shor's coefficients,
Okay.
and this is the one-off diagonal Long-Shor's coefficient.
And this part was done numerically?
So the black line is computed through the integral formula. So we know the density of states because that you can calculate. And then you plug in the density of states and you calculate using that formula. And the other one is done, the colored things are, and I've already said that that is some kind of large N limit, sort of coarse-grained kind of formula. And the actual colored things are, a recursion formula computed, it's just an explicit computation.
It's exact. The color exact.
It's the exact values.
Oh, average.
There's no averaging. This is the exact value for this finite dimensional chain. I should have written down how big the chain is, but I didn't.
The next 2 terms, different models.
Remember that there were here 2 integrable models and 2 chaotic models, and so this is showing them all.
And the A behavior is substantially different than this particular.
This one, what?
Behavior of the A is
Yes. So why is the A different? I can't tell you the answer to that. Probably I should be able to tell you why the A's grow in that way as opposed to remaining kind of stable or small, but I can't tell you.
The density of states are the E going to minus E symmetric and the A is then
It must be 0. Yeah.
at least.
So this is 0. See, this is 0 here,
Some fluctuate.
but this is not 0. This is not 0. It goes up like this, but I can't really tell you more.
And covariance means actual value minus averaged value squared.
Yeah. Variance will be actual value minus actual value minus averaged value, locally averaged value in this sense of average or
Some square root.
some squared square root. And likewise, so in that local region, right? And we'll also do covariances, which is between A's and B's.
Right. And that was supposed to stay like 1 over n. Is that right?
Yeah, there was a 1 over n in front of the formula. Yeah.
And you can check that.
Well, we're going to compare them. I can't tell you what the value here is. It looks like 1, 2, 3, 4, 5, but obviously it's been scaled by 10 to the something, and I should have put that down, and I didn't.
No, you can just do it for different values of n and c.
Yeah, of course. But
We've checked that.
we've checked these formulae backwards and forwards. This is from a few years ago. I plunked this particular one.
Yeah.
So the formula. Yeah. So we've checked that in the sense that if you look at this picture, this is supposed to be a measurement of the variance. Variance is around the mean. So this is what this is actually computing is actually variance inside. What this is actually showing is the actual value minus the black line, the mean that was there, squared. Right. So the prediction for that is the black line. And what you're seeing is the fluctuating thing is the actual value minus the mean value or the predicted value squared. And that's what's being plotted with some 10 to the minus something being taken out here. Notice that there's an n here. So maybe that helps answer the question for the scaling. Yeah. There's also 4, by the way. And the 4 is significant because you notice for the two chaotic theories, there's a relationship of a factor of 4 in the variances between the two kinds of Langevin coefficients. So that's a prediction of the prediction. That's a result from the calculation, which is also sort of borne out here.
So is it right that the variances for the integrable system seem larger?
Exactly.
But they're still under 1 by n?
They're still under 1 because the formula had a 1 by n. So there's always going to be that 1 by n.
Right.
But what's going to be is you can see that for the RMT, the saddle point equation described it well, but integrable things it doesn't. Right? There's a factor of 3, 4, etc. off. And you could say, well, you're still within in the scheme of 1 over n's, it doesn't matter, but it's a factor of 3 off.
Sure.
So, and this matters. The reason why it matters is when you have a hopping dynamics where you have large differences like this, you can have stuff like localization phenomena happening because you can get stuck in places like Anderson localization type phenomena can happen, and that can both slow down the spread through the chain.
So it could completely change that.
So it could.
And in general,
Well, that's why presumably it's integrable. Right? That's presumably this is supposed to be a diagnostic of some difference between chaotic and integrable, a different diagnostic. Again, maybe not all kinds of chaos are the same thing, but we would say that a characteristic diagnostic of an integrable system is that the variance of the Langevin coefficients will not match the RMT form. Right? So that is what we would like to say as at least one diagnostic. There's nice work by Shear, Sonner, Rabinovici, Sanchez Garrido. Adrian Sanchez Garrido is a very good guy. So good guy to keep in mind. It's a postdoc right now in Southampton. So in which they were making the point that these large variances can lead to, again, Anderson localization type phenomenon that changes the dynamics in the integrable system on the Krylov chain in some interesting way.
No, but wasn't Anderson's result in one dimension that any chaos eventually leads to localization?
So then eventually any...
But I'm saying both models, but maybe you can't go too far because you've got a limit. So maybe that's...
You mean even the small variances?
Yeah. I mean, if you went forever, everything is localized in one dimension, right? With some random stuff. But you've got a limit for how far you can go. So that's the size of the system. So you compare the two and maybe
that's the case.
Yeah. Interesting.
Anyhow, so that seems to be...
I think so. I think eventually you hit the edge. And maybe that size is always bigger than the localization is.
Yeah. So, okay. So that's another example here. So now let me give you an example of a billiard system. Because this is an interesting, this is a flat billiard. So the space is flat. So there's no Lyapunov exponent, at least for short motions, because it's flat. So this is actually a famous, we're going to consider these triangular billiards, which are famously studied in a paper by Berry, the famous Berry, and Richens. And they classified classical motion in this billiard kind of system in the following way into 3 classes. And the 3 classes are integrable, pseudo-integrable, and non-integrable. Right? So one way in which they try to explain what is going on is when when the particle bounces off the edge, instead of bouncing it off the edge, you can sort of flip it, and just make it go straight. And then you can keep doing this. And then at the end, once you attach everything together, you get some surface of some genus. This thing is called the translation surface or something like that. And it will turn out that the systems that wind up getting called integrable have some finite, have a genus 1 surface, it turns out, that you make. And in those cases, these are 3 particular rational angles that you can pick for theta 1, theta 2, theta 3. and you can solve the motion for those things by quadratures. So, classical definition of integrability. Then, for those things that make a finite genus surface, translation surface, these are general rational angles, right? What happens is that you get these beams of trajectories that split at the vertices in such a way, they bounce in such a way, that because of that splitting, in those cases, there's no global transformation that gives constants of motion. You can locally find them, but there's no global transformation to give constants of motion. You do get some level repulsion. But you have an exponential tail of level spacing. So it's somehow the spectrum looks intermediate between Poisson and Wigner-Dyson. Part of the reason why the usual Wigner-Dyson and Poisson type criteria seem a little bit misleading sometimes is that if you go look at many spin chains, the spectrum is actually somehow intermediate. It shows some characteristics of both. So then it's a little bit hard to know what to make of it. Is part of the difficulty sometimes. So many hybrid systems. So
it's not some finite and I'm just wondering. I mean,
this is a classical thing.
No, I know. No,
so this is a classical. So by the way, these things can change dramatically. You can take a classical system and quantize it, and you can get dramatic differences in how they behave. So, for example, you can take the kicked rotor and quantize it, and there was an experiment done. Which the kicked rotor, there's this thing where at some parameters, it's sort of basically it doesn't show any chaotic behavior. Then for other parameters, it finds that these islands in phase space, where we start there, it shows chaotic behavior. And then if you change the parameters some more, then it's chaotic everywhere. So what actually happens is I learned this when I gave some colloquium in Santa Barbara in KITP. I learned this from a experimentalist who I hope to run to Aspen in July. He told me he built this using a cold atom system, and instead the whole thing, the chaotic part, completely localizes and doesn't do anything. And so that's just completely weird. And so I think it's important to have some to understand. So that must be an example of a situation where you have a quantum system. If you take some limit and pretend it's classical, then the quantum, going backward, it just does a different thing.
And this is localization is another such example.
What's that?
And this is localization is another such example. Classically, if your energy is above your potential, you just keep going. Quantum mechanically, you don't.
Yeah. So I think some subtlety is needed thinking about these things. So that's an example that I won't talk about, that kick rotor, but it would be interesting to understand using these methods. Anyhow, there are also these non-integrable triangles which have irrational angles, and they have mixing dynamic, GOE-like statistics, the whole 9 yards. So we can this is calculation to sort of compare statistics just to see how the different things work. So here what I'm doing is I'm computing the standard deviation of these B coefficients, which is supposed to be some sort of diagnostic reclaimed of the degree of integrability. And this is a system where the integrability or lack thereof is heavily studied. Like spectra have been studied, everything, and we can do many different diagnostics. In this paper, we do like dozens of diagnostics. Many diagnostics. This is some paper in a statistical mechanics journal with Johanna Erdmenger, actually, and Ratnavnath Das. So one of the statistics that gets used is something called the average level spacing ratio, where what you do is you compute the energy of the next level minus your current level, divided by the current level minus the previous level, and then take the minimum of that ratio or the inverse of that ratio. Right? So you take that minimum, and that's called the level spacing ratio. And the level spacing ratio is supposed to be small for Poisson type theories. That's because you often get zeros. Right?
I'm missing. I didn't the classical billiards.
No, this is the quantum billiards now.
The quantum.
Yeah. So we've written here wave functions and everything. So what this basically, you're just quantizing a particle inside a triangular arena with boundary conditions. The wave function has to vanish on the boundary. So you build a wave function. You write down. You work out the spectrum. You just can work out everything inside. Mm-hmm. So that's why we're doing this problem. Like this you can totally do. Right? And what you find is indeed, as they will tell you, the level spacing ratio goes from small to big as you go from more integrable to non-integrable triangles. This thing, there's some range here because I don't know when I get a 0/0 if I should replace it by 0 or 1, or what the prescription normally is. So depending upon how you replace 0/0, you'll get this or this. Okay, so I don't know what to say about that. But if I leave that point aside, what you see that our variance or standard deviation of these Langevin coefficients, this is averaged over the whole chain. Notice it systematically goes down as the theory becomes more and more chaotic. So this is supposed to be a controlled set of examples that could go from very integrable to kind of less integrable to kind of not integrable at all. Right? So this is some discrete controlled set of examples is what this is supposed to be. So
What's now axis?
this is the standard. It's this thing. This thing. The standard deviation of the B coefficients.
Okay.
And the y-axis, the x-axis is the level spacing ratio, the usual kind of. Yeah. Yeah. Okay. Yeah. And so this is the average over the entire spectrum on the x-axis because for every matrix. So this is supposed to give you some confidence that in the cases where we have other techniques for understanding integrability and chaos, these measures align in some way. Okay, so this is I have 2 more examples. Right? I have time for this. I have 5 minutes. No?
Yeah.
So I'm going to do this number 4 quickly, and then on Thursday I will repeat this, and then go on to applications to the quantum gravity. Okay. Actually, I'm going to have. Oh yes. No. That's something to do with the quantum gravity. Perfect. When you think about classical chaos, actually, you think about other kinds of things too, right? You think about things like the butterfly effect. Often we think about this in terms of Lyapunov exponent. So I'm going to try to approach this from a different angle than the Lyapunov exponent. So what is the butterfly effect? Classically, if I change the initial condition a little bit, for an integrable dynamics, the trajectory will be similar. For a complex or chaotic dynamics, a small change in initial conditions makes a big difference, usually quantified in terms of the Lyapunov exponent, or the OTOC or something that talks about the initial divergence. So I'm going to be sort of interested in how it diverges throughout its trajectory. It's trying to sort of generalize from those notions at early times. So if I think it this way, I might be tempted to say the complexity of the dynamics is somehow related to the deviation in the spread of the wave function over time in the minimizing Krylov basis. And the deviation I could think of with respect to various different kinds of things. For example, I could change the Hamiltonian a small amount and see how does it change the dynamics. That's one way I could do it. So that's an interesting thing to do. Another thing to do, and we have some results in some paper with Joan Simon and Pavel Saputa on that. Another thing you could do is you could keep the Hamiltonian fixed, change the initial state a little bit, and then see what happens. In particular, an obvious thing to try to do is to say, well, look, I'll look at the 2 Krylov bases again and see how they're different, right? If the dynamics is very similar, the Krylov bases should stay not very different. Okay, so what I'll do is I'll take the Krylov basis of the initial state, that's this Ki naught, and I'll take the Krylov basis of the perturbed state. Here's the perturbed state. And I'll just expand the old basis in the new one. Right? Obvious thing to do. And then if I square those coefficients, then P and M are the probability that a new Krylov basis element is found in the old. Okay. So we'll define the coherence. I'll explain the etymology of the coherence in the K in a minute. That is SKM. And that's I'm going to take for any given basis element M. This is the Shannon entropy of the distribution of overlaps. So, of course, if the new Krylov basis is exactly the same as the old Krylov basis, this is 0. If my initial perturbation stays small, so then it's spread a little bit, and it stays spread a little bit, then this will be some small number for any M. So this is, you can think of the Krylov index M as kind of trading time, the continuous time, for some sort of discrete index. So there's I have a bunch of states, right? And so I've traded the time and this sort of changing over time, or I have these characteristic states that I need to describe what the dynamics looks at later times, and I've transferred that information over there.
The expectation would be that it would increase with them.
Yeah.
Some exponential.
For chaotic theory. Maybe less so for integrable theories, but these things are complicated, especially because, the OTOX, as we've already discussed, could possibly do all kinds of things if for sufficiently mixing dynamics that's actually integrable, So it's hard to know for sure. So that's something that needs to be thought about. So we're going to think about this. So we can also average this coherence quantity over all of the law basis elements to get an average quantity. So I just want to explain the source of the terminology in terms of some standard notion in quantum information theory. So this quantity SKM, which was this coherence of the new basis state n in the old basis, measures something called the relative entropy of coherence of the new basis element in the old basis. So let me explain what the relative entropy of coherence is. So suppose I give you a density matrix rho and some basis Bn, then the relative entropy of coherence is like this. So what you do is you have this density matrix expressed in this basis, you wipe out all the off-diagonal pieces, right? So that you decohere it. So then you compute the entropy of the decohered matrix minus the actual entropy of that matrix, and that is equal to the relative entropy of the actual density matrix and the decohered density matrix. So it's sort of, in this sense, understood as something that talks about how, the degree of coherence that was there in the density matrix, and it quantifies distinguishability between a quantum state and its decohered version. Right? So that's how they usually use it. I just want to point out that this object that we define, which seems very natural anyway, it seems very reasonable. If you take the old basis to be the basis Bn to be the old basis, and our density matrix to be the density matrix of the particular pure state associated with a particular Krylov element, then because the entropy of this thing is zero, in fact, the thing we've written down is precisely this entropy of coherence, right? This relative entropy of coherence in the old basis. So it's kind of trying to tell you how decohered or not the new basis elements look in the old basis. So just identify what it is. Anyway, so you find something interesting. So our favorite examples, I think the first person to work these things out was Pavel with Patramanis, and I don't know, I forget who. Pavel's group, Pavel Saputa, is beautiful set of examples to work out are particles moving on group manifolds, and we'll work things out there. So an example of something that's kind of canonically chaotic-ish in its behavior is a particle moving in SL2R. Or this can act chaotic, depending upon how you pick these parameters. You can also get simple harmonic oscillator type motion in some circumstances from this. Anyhow, so the way you get this is, the way you set it up is, here are your, your generators of SL2R. This is their algebra. You write down a Hamiltonian that takes this form, and then you state some representation of SL2R, just generate motion.
The group manifold is three-dimensional constant negative curvature.
Yeah. So you should expect divergent trajectories and things like this, unless you aim these things super carefully in some way. Okay, and then SU2, this is a semi-classically integrable system. Similarly, you write down some thing, and of course, the answer is going to depend a little bit on what you pick gamma and alpha to be, right? If you pick alpha to be zero, that's a very different kind of Hamiltonian. Damn, to keep it non-zero. Likewise, is the Heisenberg while this is
semi-classically chaotic, you mean Lyapunov exponent?
I mean Lyapunov exponent. So good. So then there's this coherence we talked about as a function.
But I should have asked earlier, which is I do understand how to define Lyapunov exponents if you have some semi-classical parameter, right? Like n or h bar. Because then you have a time of order log n or log 1 over h bar. And here, presumably, when you define the Lyapunovs, you do something like that.
Well,
you're close to classical. Yeah, some appropriate dimension.
Yeah, we can make this classically chaotic, maybe. So the classical motion, the semi-classical analysis.
It's easier in a sense, the classical. I was just wanting to check.
Let's say classical.
Okay.
And if you want to talk about semi-classical, then you need to keep h bar small, and presumably then the trajectories will, the path integral will be dominated by trajectories that are near saddle points of this kind. So let's say classical. Okay, so the exponential of this coherence quantity looks like this. So for the SL2R example, we're just supposed to have this interesting divergent behavior. Look at this. Go straight up as a function of the Krylov basis index. SU2, it sort of does this, and Heisenberg while which is kind of intermediate, kind of doing this. Maybe we haven't gone far enough to see what's really going on and discriminate this and stuff like that. But so this is sort of a, if you like, preliminary finding in a paper, but suggesting that maybe there's something interesting to do with this kind of method. This is all, I think, pointing to the idea that the actual structure of these Krylov wave functions is important, basically important, and contains information that I think we really haven't exploited or studied enough today.
Both these Hilbert spaces are infinite dimension.
Yes.
So you have to say a little bit about what state you're starting.
Yeah. So let me see. So I think in the actual studies we did, the states were like coherent states of the system. So the kind of thing we were doing is you take the L plus and L minus or something like this. You take some combination and you translate a state a little bit from the vacuum in some direction. What's that kind of state? What's that?
All representations.
Why all the
Particular next.
but that motion can be defined given
Can be, but I mean,
and they will just break up.
but they will break up. But so now you want to particular
The
representation.
initial state would be so
Some
all of them.
Yeah.
What's the definition of capital K coherence in the classical case?
I don't have a definition of the coherence in a classical
I was
case.
just wondering because here you were discussing classical K also.
No, so this thing, when I said it's classically chaotic, that's some statement of a classical motion on this manifold, it's a hyperbolic or not.
Okay, but
then this is actually doing the there's an EPIHT with this being Hamiltonian. So so that's all the elementary applications and hopefully give some sense of this quantity. So I think we'll leave for the next for Thursday. Late time, I'll do two examples: late time saturation of wormholes in JP gravity, understood or analyzed in this way. And the second one is analysis of three-dimensional gravity and what happens to the this complexity at late times, followed by query as to whether that object we computed does or doesn't have a relationship to wormhole size. There will be some so there'll be some question about that. Also, there will be some similarity in the expressions we get and some results in JT gravity actually by Iliesu, Mizet, and Sarosi. So there's something going on, but we haven't nailed it. So I'll just basically do those two examples, and then maybe take some time to discuss ongoing work that's been going on with okay. Yeah.
General question. These line cost states are using to define and compute the spread complexity. But often when you have a nice construction in physics, it can be used for other things as well.
Mm-hmm.
So you probably have some other applications of these line cost states. What kind?
Krylov states. One thing that I've been thinking about, we haven't done anything. So because mostly there's only so many hours a day, there's so many things to do here. But I do think that the structure of these states is going to be informative of interesting aspects of the theory. So, for example, this coherence thing was an example of it. There's no complexity being measured there. It's a question of if you construct these different basis states required to describe the dynamic, you've basically traded time for this Krylov index.
Connection with chaos. The connection with chaos. Indices.
Yeah, I think that's an interesting thing. There's another interesting connection, I think, to problems in thermalization. And because, chaos has some relationship to mixing dynamics and thermalization. There's the ETH hypothesis, which is called a hypothesis because it's not entirely, it's not proven, but you don't quite know how to prove things like that. I do wonder if we can get some purchase on that kind of question.
I was wondering about ETH. Now, that is operators that are not bad.
What's that?
You look at matrix elements of operators that are not bad, and that hasn't entered in.
All right. So, you can do that. So, one person has thought, you've thought about that, as have Pavel and Joan. So, what you can do is you can take these states, you know how they spread, And then what you can do is you can imagine you hit them with an operator and ask how the perturbed state spreads. Or you can hit them with an operator and then ask how the operator spreads in this state. So both of those things have been studied, and there's some interesting relationships within a. So far, the main thing that's been done is a particle falling into ADS, right? It looks like a particle falling into ADS and it spreads in the right way. And so that's a very nice thing. And
like perturbing the Hamiltonian.
Correct.
At a fixed
In effect, well,
yeah.
So you can either talk about that as perturbing the initial state or by perturbing the Hamiltonian with the delta function at some point at a source, and then you see what happens there. But those are both things that you can study. It's an interesting window to dynamics. There's an idea that I think for me comes from these negativity studies that you guys have done. Okay, this is the most classical basis in which to describe the system. So there's a nice idea, I think, I don't know if it was the last paper or the paper before that, maybe the way to understand the emergence of gravity from field theory is to write this very quantum field theory in the most classical possible way. And this is the most classical possible way. So in some sense, the Krylov basis dynamics should be the one in which gravity is revealed, right? So there's a sort of a program of action that's a bit on the ambitious side to demonstrate that. But what I've described here is the basis for trying to do that.
In a down-to-earth way, does it mean that this actually helps condensed matter people simulate time evolution?
That's for sure.
Okay.
That is for certain. It certainly helps to simulate time evolution, without question, right? Because amongst other things, and furthermore, it'll tell you how difficult your quantum computer if you want to do classical simulation, it'll tell you how difficult I'll say a bit more about this in the next one.
But you have to do some work to find this basis and so on.
Yeah.
That's worth it's worth the payoff.
It's worth the payoff to do that.
Use this while simulating.
Yeah. It's the nicest basis. It's the most classical basis. They save you. So yeah.
So that's.
I mean, there's something else that we've been thinking about. I don't know if I'll actually wind up getting to this. But this, I think, definitely has some kind of bearing on the question of when effective field theory should be valid on a broader front. Usually, we say effective. This is supposed to be the ending of my talk next week, which is that usually we say that effective field theory, how we define effective field theory, by saying it has an energy cutoff, it keeps states below the energy cutoff, or some length scale, something or the other. But there's a different way you could think about some of these things to say that you're looking at simple things. This is in the spirit of some of the recent things in ABCFT. But what does that exactly mean? So there is, in fact, a connection between simple defined in these kinds of ways, semi-classical defined in these kinds of ways, and then you could, for example, cut off the Krylov chain up to at some index and keep everything below that and drop things above that. And that is a kind of effective description. And that effective description will certainly break down at very late times because it will be spread out beyond that. So actually, some of the things that we've been thinking about and that we're trying to write up is the idea that at very late times, effective field theory breaks down, not because you've transcended some energy scale or anything like that, but if you wait long enough, this full complexity of the wave function, all the little ripples in it, begin to matter. And if you left those out in your description, you will not be able to talk about the physics properly. So there's some speculation / dream, you would like to say, I'll say it also in the next lecture, that if you let the state of quantum gravity keep evolving for sufficiently long, but these measures of how complicated it is, it becomes extraordinarily complicated, and the complexity plateaus at a time which is well before a Planck distance away from the singularity. Right? I mean, so there's some plateau you arrive at. It's an exponential time, but this is not nowhere close to the actual singularity. So if you take that for granted as a statement about the wave function in quantum gravity, and I will try to say something in 3D gravity about that, then you should conclude that you should stop trying to give a classical description of the system beyond that. Because the wave function is very spread out by your negativity measures, it has a lot of negativity, things like this. And so you should stop trying to describe it classically. So you should never draw the part of the geometry past that point up to the singularity. So the resolution of the space-like singularity inside the black hole it's a meaningless question. It's all very quantum mechanical. You've got to do the quantum mechanics. So that's an aspirational application that I will say something about.
Thank you.
Great. See you Thursday.